In the final part of the problem, we are trying to determine what energy values we would get if we measured the energy of this particle. So, and the probabilities for each. So the energy for the energy level n for the particle in an infinite square well, it was derived by this in the textbook. Of note, just noting that n goes like n, or the energy goes like n squared as n increases. So if we look at our wave function here, we notice that it's a linear combination of two states, both of them having a modulus of this. And the probability of measuring a value is going to be determined by the modulus squared of each different linear combination of states. So here we have a 50% chance of measuring it to be in state psi 1 and a 50% chance of measuring it in state psi 2. So one of the energy levels that we would get would be energy level 1, corresponding to the state psi 1. And of course, using this relation right here, we have the energy corresponding to energy level 1 just being this value here. And of course, the probability of getting it is 50%, or 1 over 2, thanks to the modulus here. In similar note, the other value that we could possibly get is that it being energy state number 2, thanks to this linear combination of states right here, and that being 2 pi h bar a squared. Of course, you could just simplify that again. And since it's only a linear combination of two different states, this one being 50% here, and again corresponding to this modulus here. So those are our two values that we would get. And finally, we were asked to determine what the average value of the Hamiltonian is. So qualitatively, the Hamiltonian is just the total energy of that particle described by this wave function. So both the potential and the kinetic energy. So the average value of the total energy we would get, so the average value of the energies if we measured this wave function over and over and over again and measured the average of it, would just be the average of the possible energy values, so energy level 1 and energy level 2. And again, this is only possible since these are equally weighted here, 50%. So if we found the average for that, it's just going to be 5 over 4 m and then pi h over a squared. So that is the average value of the Hamiltonian that we would get. So again, if we measured this wave function, the energy of this wave function over and over and over again and recorded the average of all those values, we would get this value here, which of note, and this is a very good test question, this value is not actually a possible value that you can actually measure here. It's simply the average. An analogy to this would just be if you had like a dice and you rolled it over and over and over again, a 6-sided dice, and you rolled it, and then you measured the values that you would get over time, the average you would get would be 3.5, which is not a value that's on the dice. So the same analogy goes for these quantum particles here. The average value of the Hamiltonian is not necessarily a value that you can measure. Sometimes it could be, but it doesn't always have to be. So that is of note, and this is a great question that I've seen used on tests a lot.